I am so happy to be back. We arranged my talk at Stanford 2020, and then everybody what happened. So forget about it. And then I finally back in Bay Area. I haven't been here for a while. I'm so happy and very excited, especially because I'm sabbatical, and this is the first week of semester. You know what I mean? And I came a little early. I visited like 5 companies and then meet a bunch of my friends and meet like the people who are pushing the boundary of the robotics. So let's get on to the topic. So this title, actually, I haven't changed for 10 years. This is actually title was on my tenure talk to the department. And that's where I started talking about this. And before that, I was talking about bio-inspired design and don't copy nature and so on. But this kind of hooked me in. This is sort of like a kind of topic last 10 years almost. Contents change, of course. I'm not talking about things that 10 years ago. So let's get on to it. So I'm going to just briefly introduce myself. I mean, there's a sticky bot, there's one of the cheetah robot, there's humanoid. And a few things. I've been defense science study groups. I've been traveling all United States secret places and then talk to those people and then military issues and so on. And also I've been advisory board member, AI advisory board member of the Hyundai Motor Group and learning about manufacturing challenge automation. I went to 4 factories, including Singapore factory has the highest automation rate in the world, and see what they're pushing on. And also overseeing how Hyundai managing Boston Dynamics and their AI institute, and so on. Anyway, so I've been in many places, and I'm also associate head of the department managing space. So last year was really busy, but hopefully that's not the case this year. And that's a quick summary of myself, and now let's go on the topic. So first, I'm going to spend a little bit of time on summarizing what I've been doing, what my previous research is, and then get on to the main topic is cognitive bias. You probably heard about this term, and then mostly from cognitive bias in AI, because AI collect the data from human, and then that basically embed the human bias. But I'm not talking about that. I'm talking about our perception issue toward the AI. When we see AI, why? In other words, I'm going to talk about why we misunderstand the capability of AI so easily. That's basically easier way to say it. And I'm going to talk about physical versus virtual because a lot of people pattern matching or extrapolate what's going on in the virtual, and then same thing will happen in physical. And I'm going to put some break on it and why that's not going to be the case exactly. And I will show you 1 or 2 pieces that could be a solving puzzle at the end. So, okay, let's go. So the first, robot outside the factory. This is pretty much sums up my first career, even including Stanford time, but mostly at MIT. And I want to emphasize the virtual services. All these big money, big tech in Silicon Valley is actually money is made by us using these internet services. Internet service means you are all dealing with the information. All these services are dealing with only information, bits and atoms. There's no energy, there's no force, no power. What I'm trying to say is like those are great. We changed our life. I mean, I'm spending so much time in YouTube, like listening these people's who already know how to collect data, and then I'm consuming. Nowadays, think about the compression data so that I can consume as much data as possible. It's amazing, but I gotta say, it's more of the good to have technology. It's convenience, in the other word, rather than compared to physical services. It's more essential. As simple as a garbage collector, like food delivery, transportation. Somebody gotta farm the food so we can actually live. Somebody has to deal with fix your plumbing issue so we can live, you can heat your house and cool your house. So think about almost every physical issue is actually essential to our lives. Somehow we're culturally, spending more and more time and money on the information services, and their focus is there. I'm glad that their attention is shifting. There's some attention growing in the physical world, but I've been talking 10 years, like, please, real issues here, especially where labor shortage is growing. And then, especially, I'm from Korea, the birth rate of Korea is like famously low. And this could be an existential issue, like society could collapse if you cannot solve the labor shortage. So I just want to point out that there's 2 different tiers of service. We have to really pay attention to the physical side. So what do you mean by physical service by technology? This is basically what we've been enjoying. Our car is $20,000, $30,000 instead of $100,000, $200,000 because of these robots. These robots are amazing. I actually recently learned that in any cell like this, robot arm is the cheapest component. Everything else is much more expensive. Setting up costs is like a multiple order of magnitude more expensive than robot arm. Anyway, they're amazing. They much more precise, never get tired, super efficient, and so on. The problem is these robots never do what humans do because there's no intelligence. It's just a position copying machine. Even as simple as plugging a cable, humans are there. Car factory is like the highest automated space in the most factories. And then average car factory has a 20% automation. 80% still done by human. And even China, they're like screaming out loud, like we don't have enough people to work on. 2015 video, I've been showing this more than 10 years now. And this is the most exciting part of the DARPA challenge. I'm not like, showing disrespectful thing about the engineer. The engineers are amazing. I'm just pointing out the hardware wasn't ready. Hardware it looks like a superhero, but all the joint technologies are pretty much copy and paste from the manufacturing robot, where position accuracy is everything, and then cannot really adapt or apply forces like a human. So my first 10 years of career at MIT is all about how can we make a design paradigm shift from this manufacturing environment where everything is controlled, we know everything where it is, high precision, solve almost every problem. But as soon as you step out of the factory, everything changes. You can't really predict everything else. I can't anchor myself on the ground, so you have to balance yourself, either wheel or leg, and you need to be able to adapt a very dynamic situation. You can't really just like close your eyes and weld, I'm done, right? So I insist that we need to have at least design has to be changed, let alone intelligence. Because I'm Stanford, I'm going to skip this part. This is the only one I explain further, but this is the Gibot, and there's a demonstration of gecko tape. I'll skip to the Keller Autumn show up. He's biologist who discovered gecko tape, and he's like calling me like, can you hang me on the glass? I'm like, you're so heavy. Can I bring my daughter? I was like, okay, fine. I'll hang her on the glass. And again, we hung 55-pound girl on the window, and then when she's out, we can just take out like this. There's no detachment force. And this is the Ice Pro, the first robot that can hook me into the locomotion. This is a soft robot, and my first and last soft robot. And this is a cheetah, finally. When I went to MIT, like I want to build a robot that can actually help people. And in order to do that, you need to have some scale. So we redesigning robot motors from scratch, controller, driver, everything from scratch. And then surprisingly, this experiment piece that cannot have a balance already exhibit human animal level efficiency, which was actually a surprise to us as well. So I'll quickly show you a video that summarizes 2013 to 19, kind of middle of my time at MIT. And this is already more than 10 years old. I'm surprised, but this video shocked many people. Most people are like surprised by the power, but people who know about robotics, they were surprised by the landing. Because at the time, people didn't believe the electric motor can actually handle the shock. And this is Cheetah 3. We scale up to be more generic looking. Before it was like, oh, can I make him like a cheetah? You never be able to do that. It become like a goat. Bioinspiration is very, very hard. This is another of my student that we've been working on, like teleoperation dynamically, destroying walls. And this is basically the distilled version of a cheetah project. And one of my students is an amazing designer. He make it like really elegantly simple and easy to build, cheap. Some anecdote, after he submit this is about 3 months later, AliExpress, there's some company selling MIT Cheetah motor at $300. And I asked my students, like, what is our BOM cost? I said, $300. Okay. I'd wear the cost motor Shenzhen and in the United States, 3 times difference. And we did some vision, and we ended up building 10 of them inside our basement lab. Literally 2 tables. I actually came down during the break, make hundreds of motors and so on. The key idea is actually propulsive actuation. Actually, there's people who taught me how to do this actually right there. Not directly, but the Ken Salisbury's student, I guess, the Phantom design was actually the inspiration. People didn't quite understand how Phantom haptic display works at the time. This is pretty much a Phantom on steroid. But a lot of force control community didn't quite understand, like, this is actually the best way to do force control, because everybody wants to achieve the accurate force control. If you give up 5-6% of friction loss, and if you minimize the inertia, this is actually becoming almost like the best force control system. So working principle pretty much same as Phantom. It's just a scale differently. We actually redesigned the motors. We can generate enough power. And this is pretty much like the haptic device in our lab. We built this about 10 years ago, and then show during the class and how the impedance control work between two arms. Because it's virtual impedance between two arms, I feel all the forces of the left arm. And the thing is, there's no force sensor. But this way, we can achieve a high bandwidth without worrying about stability at all, and then basically highest performing force control. Of course, sacrificing 5% or so error. And if you really think about how many cases you need to be super accurate in force, a lot of manipulation problem is actually more common sense and reactivity rather than accurate force control. So if I summarize sort of like my Cheetah's impact is I start developing Cheetah by the time sometime Big Dog become popular, and LS3's project about to start. All the hydraulic robots are getting like out of the world. This is not only Boston Dynamics. There's a Chinese robot there. There's a Korean robot there, Italian. Everybody's like, oh, of course, electric motor doesn't work. As soon as we publish our MIT Cheetah series, and then stopped seeing all these hydraulic robots, only thing left was a famous Atlas robot, which is very expensive hydraulic machine. And my student graduated and then joined Boston Dynamics and killed the hydraulic program about a year ago. Yeah, so they probably developed hydraulic program technology for 15 years, and my student go there and killed it. And now we see all this Cambrian explosion, all the Chinese leg robot, humanoid. There are some US company, humanoid company I visit this week, actually don't follow our principle. They add a force sensor feedback, make it complex. But I believe in the future, this is a way to go, a way to make it robust, cheap, and then high force control fidelity. So we've been modifying this infrastructure. I had a humanoid picture in the middle, but we have 5 different robots. One is a ping-pong playing robot, one is a grasping arm. They all share same infrastructure and the motor. So we literally redesigned the aluminum structure, put together a new robot in a month or two. And then because every other infra is there. I want to talk a little bit about humanoid. This is more restricted to the locomotion. Manipulation is a slightly different story, but I want to just point out how complementary are these two methods are. The RL, if you know reinforcement learning, is all data-driven. You collect a bunch of data in simulation with the proper cost function. You basically train a functional approximator, and all the memory is already distilled into this neural network. Whereas MPC, you're gradient descent every 10 milliseconds. We actually did a whole body MPC in 4 milliseconds, but we run at 100 hertz. But the pros and cons, and if I summarize it shortly, this is like a really powerful beast. It can do a lot of things really well, but it doesn't really listen to you. It's like the beast doesn't listen to you. I can't really control well. I can control this really well, and then I can manipulate, I can figure out what's wrong, but it's very fragile outside assumption. If it's a model, it's all based on models. So if models are wrong or like friction coefficient is off or something, you can't really reason about it because its assumption is broken. So it's like I call that as like a butler. It cannot do anything outside the house. Now I want to grab this butler and then make it sit on top of this monster so I can at least control a little bit of the monster. Because the problem with the most end-to-end large data approach is that you can't really control this microcontrol to improve your problems. Like I love how we walk straight and then, okay, how about turning right, turning left? If you add more, you need to retrain the whole thing again, and then you don't like something about it. Like, oof, I want to fix it. And then you start turning this knob, cost function, and then once you fix that, and everything else start breaking, and then you have no idea what's going on. And MPC, you can do that. The problem is there's no memory. You just make the same step, and then you make another step, and then you're doing still gradient descent to find the optimal solution. You just did it a half second ago. Why you have to recalculate everything? There's no memory. So there's definitely an advantage of combining this. That's actually a major focus in our lab. And I'll show you some of the effort. And this is the first attempt, which is the dynamic cost function. The cost function is actually built by dynamic model of our system. So it's a state-based. So the cost function is actually evolving, changing depending on where you are. And I have another method. I don't think I have time to explain, but this is a pure MPC. It's a whole body MPC. Running whole body MPC optimization, sequential optimized QP in about 4 milliseconds. So we can run about 100 hertz. And again, it's all cost function based. So, keep height up. Great thing about MPC, we can compose easily. Like imagine doing this with the RL, you have to retrain, recreate all this behavior and collect data. That is trajectory optimization combined with the MPC. So we can actually stitch very easily well. That's a great thing about MPC. But again, when it comes to like uncertainty, the data-driven is a lot better. So we're trying to combine these methods as much as possible. Another method we're working on is residual learning. All these RL, as you know, there's no way I can meaningfully initialize. So start with a 0, and then go with like doing random stuff, and then eventually evolve. Why do you start with MPC? Why can't we just start from known policy, not perfect, but much better than doing random stuff? So we actually can put together in a MPC plus residual RL. The problem is all these QP solver only run on CPU and much, much slower than all these GPU-based simulation tool. And our lab actually developed things called the QSADI. It's a CUDA QSADI. And then we kind of figured out how to parallelize QP solving in the GPU. So we're actually running full body MPC in real time, 5,000 in the straight, in the parallel. So we're actually doing QP and reinforcement learning, training, exploration, almost same speed. So now we can easily mix it up. I did a lot of external events in DARPA Challenge and so on, and I'll jump into the main topic, is the cognitive bias toward AI. This is probably the most important thing, and then this topic really has been in my head for at least last 10 years. So first three principles pretty much explain why we are misunderstanding AI, and then number 4 is more like describing bias, but also at the same time, it's the biggest challenge in our AI. So let's get started. The first one, we judge the performance AI in our standard. Every time I show a video of mini cheetah, and when I show you this like walking video, and everybody's looking like this, and every time I jump backward, whoa, super excited, and then like, wow, that's really cool. I'm not saying this is cool, backflip is cool, but I gotta tell you, this took about 3 days of 2 undergrad working in our lab. This takes about 2 years of my entire team working on MPC tuning the parameter system, state estimator right, context detection right. And you don't immediately see that. Even though you worked on robotics for many years, in 1 second or half second, we are pattern matching machine. We are social animal. We are evolved to judge everything based on how we judge each other, because that's a critical function for a social animal. And then things we don't really know, like if you evolve to be animal and then you see all this, like there's no data, you're automatically using your most common judgment, how we judge a human, to plug into it. Just imagine when the first time you play with the ChatGPT. Think about it, right? Whoa, like if it's a human, like how you can judge, oh, this is very smart, right? You're purely just based on like, oh, smart, oh, this much smart, oh, not so smart. You're just doing it without even thinking. That's just our ingrained function is hardwired, because this is how we evolved. I'll show you this and just think about what you feel in that second. Don't think, just feel. What you feel that half second. You probably feel like, oof, that's aggressive. That robot looks like poor robot got kicked, right? If you go to YouTube, if you look at the comments of this video, more than 60% is like you're gonna be first one who killed by the Cyberdyne robot. Why you're doing that? You're such a bad person. Blah 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 blah. Because this is how we're programmed. No matter how long you worked on robot, how many times you program robot, this is our innate nature. Like imagine you're 10,000 years ago, there's no civilization, you're in the mountain, bears running toward you, what are you doing? Like calculating how big it is, running, that's about 40 miles per hour. No, you're just aggressive, run, right? That's a pattern matching. And that's basically your old brain, your system 1, and then nobody can get away around it. But the point is that it is really causing a lot of bias when you see some AI behavior, ChatGPT, or even some humanoid, or even quadruped. And you got to be super, super careful because anthropomorphism is one of the important functions as a social animal. That is basically, we're judging everything based on human. And that automatically explains Moravec's paradox, famously said in 1988. And even that professor who thought about this AI problem used the word intelligence for playing checkers. And then he didn't say it, but the perception and mobility is kind of underestimated. Oh, that's not so important. Just think about it. Are you guys biased? What is intelligence? Just think about it. I mean, yes, we have our own judgment, like, oh, he's intelligent, not intelligent, as a human standard. But if you just step back, think about intelligence from the beginning. Like, let's say you're God, you're thinking about from scratch, or building robot. You're like building robot is playing God. All the things we cherish as a humanity, all in the Middle Ages, like who can write or not, that capability literally, distinguish this class of people, right? Oh, noble people know how to write and read. Who does math? They're just such a sophisticated people. Playing chess, play chess, you're so smart guy. We thought Isidore is the smartest person in the world. Maybe he is, but, the thing is, all the things on your right is already conquered by a computer. Yet, things we don't even think about as a part of intelligence we're not even scratching the surface. And have some perspective. Things we've been like, oh my God, that's such a cool thing, smart thing. We're only doing at most 10,000 years. And these things on the right, this thing we've been doing hundreds of millions of years. Of course, this is so, easy for us. We don't even know what's going on. This thing, we're all mostly conscious behavior, unconscious behavior. So we don't know how to judge how difficult these each are. That can be intensified by how your brain works. Title's weird. You don't know what you're doing, but I can guarantee you don't know what you're doing. So this is like 3:30. So everybody had lunch, right? Can you raise your hand if you eat lunch? If you eat lunch with someone else talking and raise your hand. Right, most of you, socially active, good job. But just think about it. Have you, I know not many of you ate carrot, but just imagine you ate a carrot. If you hate it, it might be trouble, but anyway, just assume you bite a carrot. What happened afterwards? Have you thought about eating as a process? Robotic process. Anybody can control individual teeth? That's creepy, but anybody? No, right? That's not right. You have basically two rigid body, maybe 2 to 3 degree freedom, chop down the carrot. You push the carrot to the teeth, crush it, maybe turn into 3, 4 pieces and small pieces. Small enough, I'm going to swallow. This is too big, I'm going to throw into the teeth. And then you're eating. Think about some people eat really fast, right? This is happening while you're talking to your friend. How many robot arms do you need to do this? Your tongue, your tongue is doing all that. And do you remember any of this action during lunch today? I'll give you another test. Grab something from your pocket right now. It's a little tricky because you're sitting on it, but just grab something and then show report. Go report to the CEO, show it to them. And I'm 100% guarantee almost everyone use your index finger. What trajectory did you command to your second joint of your index finger? Anybody remember? You just did it. You believe that you can control your finger, right? But you just don't remember what you just did 2 seconds ago? You don't know what you're doing. I'm just proving it. Because these are happening in the subconscious level in cerebellum. Your forebrain, you're sitting in the CEO's seat, chairman's seat, and you're just commanding a very abstract level. And all this concretized, detail, devils in detail actions are happening somewhere else. I don't know where it's going on. Neuroscience don't know where it's going on. I'll show you a little bit of creepy picture. So if anybody very sensitive, graphically sensitive, maybe like ears. This is the famous chicken called the Mike the chicken. It happened in 1945. I read this paper when I was graduating in Mark's lab, and I was like, that can't be real. There's known to be living for 18 months after head chopped off. So this owner feeding waters and grains through the throat and then touring around making money. And then I was like, that must be some legend. It's not gonna be real. Until I found this video in the world of cell phone. Same thing happened and somebody captured it. That's behavior you can achieve without head, technically without forebrain. So they actually respond. Like if you poke it, it responds. It almost tried to peck on the ground. If you look carefully, actually one vestibular organ and then small brains are intact. Those are attached to the body. Those are controlling the body. Maybe we don't need the CEO for a company. It's still running, at least for a while, right? But the point is, your forebrain is not aware of these actions. So I was very curious, like, do I know? What's going on? So I asked my grad students, one of the events, I was like, can you take a video, slow motion? I'm gonna just grab this. So I will show you that video. That way, we can at least kind of inverse, learning what the cost function is were and so on. So this is what happened. I'll show you one more time. It's too fast, so I slow down, and then I'll show you what happened. You throw a hand. A lot of times you just throw a hand because our hands are so compliant, and then you're so adaptive. And then that's how you grab something. Nobody grabs something by doing this. This already looks weird, right? Because identify, and then you already head is towards something else, like where to put it and so on. You crash it, and then just think about you're writing an algorithm, like which one to pick. You have a tactile sensor, identify locations of fruits. Probably you're going to have something like highest, closest, that kind of heuristic cost function, right? My hand somehow is much dumber. You just open my hand, and then by doing it, it roll out the best candidate. And then my finger ended up touching 5 more. And even at this point, if you have a right algorithm, you'll probably go for that one. That was the highest, closest, right? I was very disappointed. My hand was much dumber, and it chose the worst possible choice. I have no idea. It's digging, and then it finally put 3 fingers on this fruit, and then somehow I don't know which part of my body realized, it might not be secure enough, and then dive in. So I was like, each step seems really dumb, right? It's not very optimal, right? None of them seems very optimal. But you remember seeing 3-4 times of change. Plan A, plan B, plan C, plan D, right? The whole thing happened in about 0.7 seconds. Do I remember any of those? Of course not. Of course not. I don't know any algorithm or AI can do this kind of stuff and this fast. Is there any chasing any optimality, like gradient descent? No, not no whatsoever. If I grab this fruit 1,000 times, I'm pretty sure I'm successful. Not every grab looks going to be this complex, but I'm pretty sure I'm 1,000% successful, and I have no idea what I did. This thing is also caused by our learning. We are animal. We communicate through language, learn from language. We describe through language. We talk all the time without really realizing how abstract these tools, language communication tool is. You guys probably learn a lot about communication tool, why we have a fight with your spouse or girlfriend, boyfriend, and there's a lot of miscommunication because our languages are so abstract. It's not very concrete. That gets really worse when the word are describing some action. It's the actual worst. Like spread the peanut butter jelly. Just think about it. If you want to teach a little kid how to make a peanut butter jelly, what would you say? Grab a bread, scoop out the peanut butter, and what are you going to say? Spread. And what else would you say? Would you say sin x plus minus force profile? None of that, right? That's all you say. And look up dictionary with the spread. It's crazy how abstract the word is. It's almost like, you increase your entropy, right? And we are okay with it. We're kind of adapted with it because we see each other. Sometimes you learn without even seeing, but we have this way to get this very abstract concept and then concretize through this complex machine, our orals. we don't have enough word to describe these actions. Good luck language model solving robotics problem. Why? So I thought of why our languages are so lacking. I realized we have things, this is only probably one piece of problem, one piece of reason. We have things called the mirror neuron. This is an experiment a long time ago when neuroscience measure where the activity is going when a monkey eat the banana. And then constantly measuring, and then what happened when the other monkey eat the banana and the same part of brain just activate. So they call that as a kind of mirror neuron, AKA empathy neuron. You feel basically what other people. This is scientists said, this is why you're excited when you watch basketball. That's why you're crying when you watch sad movies. When I'm smiling like this creepy, you probably feel like, oh, I'm maybe happy, maybe not. Like those things copy this simulating tool. So that's one theory. When I learn some mechanical action, I don't need to know all the details. I just learn it because the word can simulate this. So that's probably why we never developed this like detailed action language, because whereas we have so much detailed language for democracy, the Congress, and all the things we made up. When it comes to the action, we're just incredible. Somebody says clean tray, and this is what he does. Trajectory optimization or force tracking. I don't know what is the cost function here. You know, the modern AI is amazing in abstraction because there's a lot of data, reducing dimension, like encoder part. Decoding part is a hard problem. Oh, no. Recent like language image models, language visual models are amazing. I can draw all the things. But be careful, that space is so wide, and then there's not much wrong or correct in this visual world. And same thing as writing. You know, a lot of writing, sometimes hallucinate. Because a lot of other times, that sentence probably there's no right or wrong. But that's not true for physics. I will tell you a little bit about it later. The last piece, this is actually a little technical, but it's important for scientists here. We are a lot less quantitative. We make decisions not quite quantitative, whereas we can't do anything with a computer if you don't have a quantitative basis. If you don't have cost function, none of this RL transformer, nothing works, because you need to have some cost function. Even imitation learning, you have to be as close as possible with your prior, you know. And why we see a lot of Lego robots running well, but like not so much impressive manipulation, because it's a cost function. Of course, the dimension space is much smaller too. But Lego locomotion, I don't think we have a best cost function, but we have an okay cost function, which is keep up your center mass high up, keep the orientation right, minimize a pitch and roll, and then that is okay cost function for not falling. It's not the best one because you can play basketball with that. If you play basketball, your center mass go up and down like this. But that doesn't happen when you ask a robot to do it because your cost function is like keep it up all the time. But it's okay to make a robot walk. Much, much harder to cleaning the room. What cost function are you going to write? Like, do the dishes, and then what cost function should I write? Should I randomize the action and then evaluate clean, dirty, clean, dirty, clean, dirty, like that? How long is it going to take to let it learn cost function, right? And some people say, oh, why don't we, nowadays visual language model plugin, we have a limited data. Why don't you show a bunch of clean room and then try to match with it? Yeah, I think there's a pathway, long way to do it. But even harder thing to do is actually quantifying what not to do. Just give you an example. Like, I want the robot to bring a cup of water. Go for it. What is the cost function? What do you think? What would be the cost function? Anybody has an idea? Yeah. Anybody else? Like, what would be the quantifiable cost function? Yes.
Don't spill the water, or like quantifiable is how much water you bring.
That's a constraint, right? Or reward function, like Steve. Yeah. Like a reward function could be like minimizing time or minimize path, right? But is that important? What is important? What you said, like don't spill the water. Make sure you close the door. Don't mess up things inside. Don't. These are constraints. All the graduates are manually put it up and then not really describing the paper. And then like you did all the real hard job and then, oh, now I'm going to do optimize. And then see, it's optimal. By the way, the cheetah jump over obstacle video, that has a no cost function. Zero. There's a cost function is zero. Because if you're jumping over obstacle, why do you care about optimality? It's the feasibility such. That way you can actually calculate it faster. So if you just think about a lot of human decision making is actually quite binary. It's not quite optimizing. A lot of people, Euler says that. Euler says, oh, every molecules, everything happening in the world is following some kind of optimization. I strongly disagree. Any biologist here will probably agree with me. Evolution is not even an optimization process. And then some computer science students said, Sangbe, I don't think I agree. I think everything is optimization. I ask, what did you buy last week in grocery shopping? Like, what do you mean? Why you ask? Like, just tell me. I say, I bought 2 tomatoes, one pack of milk. What cost function drive you to buy this? How did you decide, right? We don't decide like that. We decide like, is that good enough? Okay. Okay is the number one words used in the, the couple's grocery shopping. Like it's a bar, is it good enough or not? Like clean your room, how you evaluate it? Not do it again. Oh, good enough. We don't score everything, right? We don't think like that. But the problem is programming like that is so hard. Like how you program automatically what not to do, which is creating a constraint. Optimization is not the hardest part. Creating this cost function constraint automatically, that's the hardest problem. We are not really operating that quantitatively. We're operating quite qualitatively. Making the best tasting pasta, like how are we going to quantify that? I'll talk a little bit about virtual to physical. This is getting very popular nowadays. And everybody like extrapolate, this is what happened to language model, same thing will happen. Let's just, gajillions of data will solve the problem. There are some obstacles. First of all, everybody knows that all the virtual data is in the web. Even labeling, a lot of labeling is done in the web so that like how often that image with that language show up and one page, what frequency is that? That kind of automatically pre-training the labeling, and then now human label to refine, and then RL, and then visual language model works. But almost all of them are already there. Whereas we don't even know how to collect data properly. I know what Tesla is doing. I'm not 100% agreeing with what they're doing. And another things people don't fully aware is all the virtual AI is a human in the loop. You're using it as a tool. Nobody like use the web AI to do something automatically. But you can just use that. You can make robot just semi-okay robot working in the factory. I'm going to hold your hand. Like what is useful for the robot is all the hardware, it has to run autonomously. And failure cost is so high. The biggest thing people don't quite realize is the execution uncertainty is so different. In virtual world, there's no uncertainty in execution. Execution side. I'm not talking about the perception and processing side, the reasoning side. Execution side, there's no uncertainty. Do you remember if I show you the intelligence map where the system 1, system 2, self-driving was right in the middle? You remember? This is intentional because driving is kind of half virtual, half physical. Because driving, if you get to the detail, representation of the world and then execution trajectory, if you know what trajectory is right, executing that trajectory, uncertainty is near zero. Not quite zero, very close to zero. Almost every car, unless you're like racing or driving in the snow, the chance of following the trajectory is almost 100%. Not quite, but close to 100%. When it comes to manipulation, that's not the case. Because you don't have a perfect model. Even though you collect gajillion data from simulation or real world, you don't have a perfect model. Every making content, breaking content, you have uncertainty. Which means planning is not enough. You need some fast local feedback. Somebody says that, even planning, if you do plan quickly enough, it's a feedback. Yes, but that never run really fast. You need to have some grounding, stabilizing algorithm under the planning. If you just think about company, company chairman says, that looks like a good plan, go ahead. That's not always the case. There's a hidden feedback loop of that person. Oh, I would figure out this way, right? There's always like a loop going on, fast loop, medium loop. If you're aware of this, you might be ready to talk about behavior cloning. I know many of you already work on behavior cloning. I have to explain this, especially those who don't know about behavior cloning, because you're going to be fooled by it. Why? Because these are pretty impressive, but more so, this video from Stanford, she was Columbia, but the Shiran-sang's video, I was shocked when I first saw the video. This is the most impressive video I've seen. I believe I'm still showing this as an example. It's amazing work. All these big techs are actually adopting, and then it's almost like changing the robotics world. But I gotta explain based on how I interpret it. If you don't know the behavior cloning, especially for Yumi case, they're actually collecting data like this. They don't even need a robot. They just collect data with the cameras and 100 times or so. And then this is what happened to robot. When it's about to clean and Gretchen pour more ketchup, and then, whoa, wait, this robot recognized that's a dirty and cleaning it. And when it's done, it closes water, and when they open the water, it closes it. When I first saw it, I was like so shocked, and I was like I was goosebumps. Like, oh my God, they did something amazing. And I read the paper, and they're like, oh, I see. So those who know already behavior cloning, I don't know what to explain, but those who doesn't know, I will say it this way. This algorithm basically is as if you watch Indiana Jones 100 times. I know nobody will watch Indiana Jones 100 times, but just imagine you did that, right, 100 times. And if I show 2 seconds of clip, you will know exactly what happened next clip, next second, right? So that's basically what this algorithm is doing. You just look at 2 seconds and then, prediction of the next flip. That's why it's recovering, like catch up, and then go back to time, and then, okay, that's next to do. But if I ask you, what happened that Indiana Jones actually crushed by the stone and then died? And then what happened next? No one can answer that question, right? Because you're only watching the movie. That's the scenario following. And the same thing, if something happened, let's say ketchup was spread not at that time and some other time, doesn't know what to do because you're off the scenario. That's basically what behavior cloning is, with a little bit of fuzziness around it. So I'm going to skip this. So if you really think about it, the imitation by itself is not really a proper policy learning. It's a little weird because everything is policy learning, but I'm saying it's proper policy learning. I will give you an idea. If you have all the detailed data, like ground action force, everything, joint angle of 1 million people walking in the street, million hours. If you have all that data, do you think you can make our humanoid walk on flat terrain? What do you think? I'll give you like 3 seconds. If you don't like it, make it billion. Billions of people, maybe that meant too much. Anyway, millions of people for 1 million hours. How many people think we can make a robot walk on the flat terrain? How many people think we cannot? I don't know. I never done it. Probably we can. But I know what happened if I shove it.
It will fall down.
It'll fall down because there's no data. What do you mean? If you follow 1 million hours, there must be somebody got shoved. Yes, how many of them? 3. Is that enough to train a policy? Point is, all the teleoperation data is expert data, which means these are all successful data. Beautifully crafted scenario of Indiana Jones. There's no fallback scenarios not there. There's no way you can learn how to recover from all this uncertainty. My wife works on kitchen years, still she drops something, we drop something here, we recover something, understanding what's going on. My son is still learning, and so on. You have to create every possible conjugation of all these scenarios with the labeling too. Just think about it, right? So that's why imitation only, never gonna learn proper imitation, the policy learning. Surprisingly, I found this quote by Oscar Wilde, who doesn't know anything about RL, but this is what it says. The imagination imitate, but the critical spirit that it creates. Just think about it. RL, it sounds like RL, right? RL is more like it's critic, actor critic is going on, right? So RLS definitely have a better policy characteristic, but it has a cost function issue that I just mentioned in number 4. So how are we going to handle this problem? So if I simplify the AI world right now, we have amazing progress in language model. I'm still like struggling to understand how that do the logic and reasoning, and then combined with the video is just unbelievable. Maybe you can tell robot, okay, showing the video, grab that apple, and then probably know how to roughly throw my arm. That trajectory might come out from language visual. The problem is we don't know how to ground that action to complete the task. Last mile problem. You know, the logistics, like, you know, last mile problem is the detail is very hard to do. And you can also think about delivery 10-meter problem, how to get out of the car, bring the box, and walk into the house. And you can also think about last meter problem. You have to grab the door, open the door, throw the box without breaking it, and then close the door. If you think about all this task, simply delivery, the variation is just growing like a tree. It's like a fractal. When it comes to close to the end, the variation just explode. Same thing happens in manipulation. Like if you grab something, you know, it's very easy to plan. Like I know the location, I can do the plan to motion trajectory, but all the detail upon contact and what I have to do, there's just so many variations. I mean, sometimes easy, sometimes difficult, but that's where we're basically missing. That's what the language visual model cannot do anything. We have to really bridge the gap from there to real guaranteeable action. And this is only one piece of advice, and I've been working on this in my lab several years. We need to create an intermediate representation that bridges the gap of language to the real world, because language has a limitation of representation. It can't go down any enough. It's too high abstract. So I'm going to call that sticky reflex, for example. It might have some parameters. And good luck describing this in human language. Oh, I saw a really cool video. What was it? You have to use your arm probably to describe it, right? And another reflex, this is actually a pretty useful one. It's called a gliding reflex. It's not avoiding, it's actually keeping distance to object. So we don't need to plan ahead of time. When you grab something, you're not planning, I'm going to move this finger 45 degrees. We don't do it. We just throw a hand and grab it. So this, hopefully, we can make the planning easier and more adaptive, not relying on all this high-level planning. That way, we can do quickly and we can adapt. So this is one example. I wish I have more one, but this is still the best one from our lab. It's a real time. There's no sped up or anything. And the algorithm is a dumb, simple, just like a YOLO downloaded and then like identify cup click and then inverse kinematics, that's it. There's no grasping, trajectory optimization, no behavior cloning, no RL. Everything's local, basically. There's some state machine, take care of like, did you grab or not, and so on. But that way, we can actually, we don't need to specify all the detail from the data. Data only need to say, there's a apple, just reach there. And then rest should be taken care of by this low level. That way, we can really ground this language visual model to the real world. I'm not saying this solves everything, but this is a way, a high-level philosophical way to think about it. So I'm a big believer of a hierarchical system like a real company. The reason why a company works a certain way, you need to react quickly. I can give you an extreme example. Like, imagine there's a building fire, and then the company worker, office workers writing email to CEO. Can you tell me what to do in an optimal way? That's basically all end-to-end algorithm is doing. That algorithm sense everything, optimize everything, act everything. That's not how it should work. Like, you have to be hierarchical, so local things should happen quickly, tens of milliseconds, and then high-level planning doesn't need to run that fast. That's basically what happens. CEO, let's do this once in a quarter, maybe a year, and then locally you're adapting quickly. Oh, something changed, snow, rain. That's how we built our company. Our intelligence should work that way too. I believe human brain works that way too. That's why I have no idea what I did when I grabbed something in the pocket. Another thing I want to tell you about the difference between language and physical action. Language is inherently imitation. What do you mean by that? If I say hello and everybody, whoa, that's weird though, right? You have to be very similar. We're social animal. I need to say exactly. My son is copying me and my wife and his friend to be as normal as possible. Definition of a meaning of a language is a stochastic by nature, because if people say a words more in that context, that's how we define the words that change over time, right? So inherently imitation, inherently stochastic. Fantastic for computer. So we have to respect agreement among people. In physical world, we're not quite imitating. Like how many people learn things grabbing from the pocket you just did, watching, I'm gonna see how my father did. I can't see anything because it's inside a pocket. Nobody learned how to do that looking somebody else is doing, because in a lot of these physical actions, you have to respect the physics. Not trying to fit in the middle, imitate everybody else. Yes, some special case, golf learning, like weird, like sports, you have to learn by looking at it. But a lot of physical action, we kind of learn naturally. We don't know how it works. Probably somewhere in cerebellum. That is basically a huge difference between language to action. That's why we need something like this. I want to finish with this. Labor shortage is really scary. I don't want to, make you feel like future is doomed. But like the global warming, I think we have several decades. Labor shortage, I think we don't have that much time. What's going on in Korea, what's going on even China. I thought China is abundance of people. They have a struggle to find people, let alone United States. I've talked to many factories in the United States. They have a lot of problem. This is takeaway, and I'm ready to take any questions. Thank you very much for your attention. So do we need to use a mic, I guess? Or?
The room microphone.
Oh, okay.
Yeah.
So yeah, feel free to ask any question. Non-technical, technical, yeah.
Do you have any ideas what this intermediary abstraction between language and between the robots and the physical world might be?
I'm architecting right now, and I'll tell you when I have a better.
Okay.
Yeah. I'm still looking. I've been thinking about this many times, but nowadays I have a better idea. I'm doing it, but I can't tell you too much at this point. Yeah. Yes.
A question about the idea that we don't have a cost function when we buy groceries. When you say something is good enough, or even in cooking, would you not say that you could say there's a cost to how much effort it takes to specify something else? Like, oh, it's not worth the trouble of doing more.
Yeah. But what I'm saying is that we don't care anymore once it passes a certain bar. We're not minimizing all the time.
And that's not quantifiable as a cost of, I don't want to put
So
this
it's
much thought into
so more like a feasibility search. Is the feasibility part of optimization? Yeah, sure, we can call it optimization. But once it's feasible, we don't care too much. Just think about evolution. Like, oh, cheetah designed to be like optimal for running fast. No, as long as you're faster than prey, you're done. You don't need to be faster. All the evolution is like, so the evolution is described as a fittest survival, right? Survival of fittest. I don't actually agree with that. The best way to describe evolution is like survival of happen to be good enough. That is more accurate description. It's a bar. Did you survive? Did you have an offspring or not? Maybe you have more offspring, I guess. But anyway, yeah. Anybody else? Yes.
You mentioned the importance of the feedback policy. Do you think there's a hardware challenge that we're facing, in the sense of sensors that are able to provide that?
So how I see it is, I get this question hundreds of times. This is how I see it. Imagine you're building a house. The house basically is a full AI system. Architect design a frame and a room where the room is. And the frame, the structure frame is basically hardware. And after frame, you build the wall, drywall, put the furniture, and I don't like this structure. Then you have to start over again because your frame is wrong. So I'm not saying hardware is going to be bottleneck, but if your hardware is chosen wrong, you might have to start from scratch. Furniture can change. Software is easy to change, but everything, painting, all that is based on the frame. So the hardware has to be chosen very carefully. I don't think we are not going to be able to AI because we don't have this magic hardware. But we have to choose very, very carefully. And do we know how to do it? Not yet, because this is a coupled problem, right? Hardware, software, we need to choose and try it and so on. Yes.
So one might be a minimum but general problem formulation for physical intelligence, like a test or a bench that can advance the physical intelligence problem.
Test or bench?
Task or think of MNIST. So can you think of one testable problem? So once the robot solves this problem, we can say it has a physical intelligence kind of thing. So the problem is there is a lot of fantastic demos, fantastic things,
Yeah.
but the problem is we are not sure how we can generalize. So
No.
it will be great if we have a minimum problem, but we know once we solve this problem, it will do many other things like that.
Like a Turing test for physical intelligence.
Yes, similar, yeah. But yeah, minimum like benchmark.
I mean, I can think of like most fundamental thing, grasping. I remember Gilpress has grasping solved in 2012 or something. I don't think we have a general grasping algorithm yet.
So what do you mean by we don't have a general grasping algorithm? Because I see a lot of videos robot picking up grasping things. So
Staged though.
what's the difference?
So you grab your kid's toy box and then throw it in front of the robot. You wouldn't be able to pick out that toy buried under another toy. Unless it's trained that exact scenario, because all the demos are based on behavior cloning. They're following the scenario. Yes.
You're just talking about how you've been visiting a lot of companies,
Yes.
spending a lot of money
Yes.
trying to solve this problem.
Unbelievable. Yes.
And I'm just curious to see, do you think they have the wrong success cost function, or why do you think?
I mean, I can't say what I think it is, but I can guarantee what I think is right. How I say is, there's the range of company, company, Google, a lot of money and then do research. But certain type of company, more like a startup company, once you start, you need to run because you're running out of time. So they need to make a best hypothesis based on what they know. They probably need to know what they don't know. And then they have to go for it. And some company, even though they're big, they run like startup. I'm not going to say what. You probably know what it is. But anyway, just run. You have to run. But if you have enough resources, you can pivot when you realize that's not the case. So in my personal view, they're kind of not perfectly aligned, but some of them have enough resources to pivot. So we'll see what happens. Yeah. But it's very costly, yes.
Hi, I have a question about, a more practical question about robot learning. So you mentioned that if you're just learning from pristine, perfect expert data, you'll just never have the robustness to actually deploy.
Yep.
And indeed, a lot of behavior cloning works, including Umi, also understand this fact and adding a lot of recovery data. So one thing that's very common in every single kind of imitation learning algorithm, whether it's like learning from language or learning from actions, it's the same. You have to kind of engineer the data to provide things that push out of the distribution and comes back. And so, for instance, in the dishwashing example, we literally collected examples where the robot finished washing the ketchup and we put in extra ketchup in a way. And so, although that doesn't cover every single case,
Exactly.
it does seem like that's a pretty practical way to cover the most common cases. That is almost good enough.
So let's think about this. Let's say we cover the dishwashing problem. Does that help at all in organizing your fork and spoon? Not at all.
Not that simple.
So think about how many cases we're talking about. How many variety of tasks with train without labeling. You have to label them so that make it meaningful. Do we know how to label them? Absolutely no idea. Good luck labeling spread. Otherwise, it's a piece of trajectory when that's some video. There's no meaning. There's no semantic meaning of that data.
How much semantic meaning do we need?
To be able to understand. Language model exists. They're ready to engage. You're separate from language model, right? All these language amazing understanding is there, and our data is running separately. That behavior cloning knows that that's washing, or does knowing rubbing, or stacking? No, it's just a piece of trajectory. You're chopping down every 40 millisecond and some trajectory, and what is semantic meaning of it? We don't know how to tokenize action. Language is already tokenized. We know how to tokenize image. Image is convolutional neural networks, we're done. We don't know how to tokenize action. Meaningful way. Anything else? Yes.
15 years from now, what's it going to look like?
I believe still many companies are trying many things and kind of pushing, like, teleoperation sneak in there to make it looks like it's happening. And I believe self-driving might be done at the time. My son doesn't need to learn how to drive. I still don't know when self-driving will become real, even though seems very close.
Worldwide?
Say it again?
Worldwide?
When?
Worldwide? Self-driving in any country, in any kind of...
Why? Oh, it's a long tail problem. Like this, we're so close, but I don't know how.
I mean, do you mean it will be solved everywhere?
Yeah. With in 15 years probably, yeah.
Sorry for interrupting.
Yeah, no problem. And another piece of information you might be interested in. Tesla, I'm saying it, a specific company, have a 7 million teleoperator they don't need to pay to train a robot that has only 2 degree freedom, dealing with only one object, which is flat ground. We're still not quite there. Manipulation, we need at least 10 degree freedom, dealing with the infinite variation of object and task. Right? Driving is easy, moving A to B. What we do with the object is just almost infinite. How many teleoperator with the robot pair do we need to collect how many years? Just think about that. Elon said 10x. I'm completely disagreeing. I think we need at least 10,000 times more, which is tens of billions of robots. Tesla successfully sell the car first, so collect data. Can we sell tens of billions of humanoids first and somehow force them to teleoperate? Just think about it. Yeah. The current paradigm, current paradigm. I'm not saying that's what it takes, impossible. No. We will figure it out to a more meaningful way. If you follow current paradigm, that's what it takes. Yes.
What's your favorite, most difficult manipulation task?
Everything is difficult, but I'm still obsessed with the picking. Yeah. Yes.
I'm sure you enjoy your job, but if you had $1 billion and the ability to have a startup, why aren't you doing that? Do you feel like it's not ready to receive $1 billion and to go? Do you feel like it's not mature enough?
I can have a separate session with you about PC world and all that, but I think it's a hypothesis. If you have a really strong hypothesis that nobody has, and if you believe it, you should try. Because no matter how you sell your company, sell the idea, raise money A way, B way, getting money from customer or getting money from VC, selling big dream, that is not that important. What is important? Do you actually have that hypothesis or not? Because if you don't have it, either way you're going to fail. Unless you're super lucky that puppet show and then sold by big tech, but in proper way, you're going to fail either way. If you have it, most likely you'll succeed in either way.
Beyond autonomous driving, do you see any other use case of the current technologies that might get cleared faster? For example, in case of Tesla, do you see, because they have a controlled environment within their factories, these robots may actually find some application which is useful to them?
So I've been 4 factories, and I talk to everybody. I can just tell you one thing. You have to do unstructured picking, more pick and place. All these demos, they're doing structure picking, which can be done, is been done already in current robot. So about 20-something% of the things, they're manually done. We have a technology we can automate tomorrow. The reason why they don't automate them, because it doesn't give you ROI. They might change in the next 2 years. It costs millions of dollars, so they want to have ROI. If you have technology, they can adapt, change the parts, like, oh, I changed the design, and still be able to without reprogramming it. That is the important. It's not the important shape of human or having leg. Doesn't really matter. Whatever that manipulator, robot arm, can adapt the variation without reprogramming, because programming is that's an expensive one. Robot arm is $40,000. The program that robot to pick up moving in the current factory costs $100,000. The stupid linear rails like $200,000. If you look at a cell, the setup costs about $3 million-ish. Robot arm is $30,000, the cheapest component. The programming is about 4 times of the cost of the robot arm. So flexibility, your algorithm has to be flexible, adaptable enough, but the thing is you have to reach 99.9% of robustness in the factory. Then it's gonna do the magic. But that's really, really hard bar. Doesn't need to look like human. Probably doesn't need to have 5 fingers either. Any other question? Yes.
Does it need to have skin?
Good question. I don't know. I think the softness is helpful when you do things fast, right? Humans are so fast, right?
Distributed sensing?
Good question. Probably. But one thing I can tell you, in factory, things wear out because they're doing things all the time, especially robots. Human doesn't do that, but robot does like million cycles and so on. Things wear out. So they don't even want to put a rubber pad in there. So if you have a tactile sensor, you have to really focus on how to make it robust. When it comes to home robot, maybe that's not as worst, but the factory is very, sensitive on those things. Creating a dust is also, they don't like it. It's tricky business, yes.
Can you tell me your opinion about model-based reinforcement learning or approaches to learn world models from the? Yeah.
I mean, when I first hear like, oh, collect this infinite data, build a world model, and I was like, that doesn't sound right. But to some level of abstraction, I think that could be very useful. Not the physical level, like just the high level, language to visual, like, as I said, like grab that cup, a bottle, and then you create that video. And then while creating video, you don't need to create video, like you can kind of create that trajectory. So robot can at least kind of mimic that without even doing any, because reaching, we don't need to have a stability issue, any cost function issue. So a lot of planning can be covered by mimicking. So, but I don't believe world model solve everything. That's just impossible. Yeah, just space-wise. Yeah.
We should actually go.
Yeah.
So I think we should
Yep.
wrap up and take more questions at the happy hour.
Okay. Thank you very much. Yeah.